I'm going to try to and attempt to explain to all of you that you can mix oil and water together to obtain a completely colorless and blended solution. So, does that sound weird?
Mm-hmm.
Yes, it should sound strange because oil and water are liquids that just don't mix. And this is how oil and water are liquids that don't mix. Quantum physics and biology are two sciences that are generally believed to not mix at all. And well, I'll just start with a general introduction of what the two sciences are for everyone in this room. So, biology. It's the science of how life works, how living organisms behave with other living organisms, and how living organisms work itself, with like the cells inside them and the mechanism of all these cells. So basically the science of life. That is biology. And on the other side of the boxing ring, we have quantum physics. So in my opinion, quantum physics is a branch of science that likes to overcomplicate itself for no apparent reason. Yeah. So this is not necessary. All you need is this. Quantum physics is a branch of science concerning the behavior of extremely small particles. So you look at really small particles, the smallest particles of matter, you look at atoms. The smallest particles of energy, for instance light, you look at, quantum physics looks at light in the form of photons, we'd call it. So the smallest possible divisions of matter and energy, that's what quantum physics deals with. So now there's an interaction to demonstrate the kind of relationship between quantum physics and biology. Suppose I asked a physicist to make a calculator for me. So the calculator would be able to add up any science together, right? But if I ask the calculator to add up quantum physics and biology, it gives me an error, does not compute. So I can demonstrate this even further because during my Christmas holidays, I went to the Oxford Department of Physics and I had a fruitful discussion with Mr. Subir, who's the head of particle physics at Oxford Department of Physics, and I was hoping that, I finally met someone. He has a lot of information. He's a wise man. I'll be able to get some knowledge about quantum biology. So I asked him, "Do you know about quantum biology?" And he said, "You must be joking, right?" So this is supposed to show that it's a lesser-known topic, and it seems counterintuitive to those few scientists who actually hear about it. They dismiss it right away. So in all of his years of research or expertise, he hasn't even come across the term. This is why it's quite hard to actually research this topic. So let's just start with why I decided to choose this topic, which seems really bad initially, but I'll tell you why. So the first thing is that my head has this fascination with forming links, networks, patterns, whatever you'd like to call them. And because of that, my favorite sciences are biology and quantum physics. So when I was thinking about a possible link between the two sciences, that made me really intrigued. And although the idea sounded absurd to me, I found that there were many articles and news articles about it online. So even though it was thought not to be possible, there's evidence for it, and that evidence was yet to be fully explained. It was mysterious, and that's what I liked even more. And the last part is, of course, I love science. So this may sound silly, but this is what I think is really important. Whenever you're picking a topic, any topic you want to research about, you need to be passionate and you need to be interested in it. Because if you're passionate about the topic or subject that you're choosing, then you find that not only does your research momentum stay constant, but you find that it may even increase, as it did in my case. That I found myself being more and more curious about the topic, and I found myself getting more interested in it. So let's talk about a bit of my research process now. So how exactly did I research and where did I start? So for my topic, I decided to go with an ordered progression. I first started with a really simple book. This is a physics A-level textbook. You might think that, that's too simple for this topic, but this is exactly what I needed. I needed a fundamental, basic background to learn how I could explain this. And once I knew a bit about quantum physics from my A-level textbook, I went to a bit more in-breadth books. These books, this first second quantum theory is not really sophisticated nor scientific, it's not in-depth, but that's not what I wanted. What I wanted was a wide breadth. And this provided this wide breadth to me. It acted like my map. And because I had this breadth, I knew exactly what I wanted to research for my topic. So I went on into more in-depth stuff, which was impossible. So in this book, it was more that 50% was explaining how it works, and the other 50% is speculation. So 50% was the one that was useful for me, but the other part I was speculating was still useful in the sense that I could learn about certain applications of the topic, and that is still useful to me. So the idea is, once you start from the smallest and the simplest, you climb your way to the top of the mountain, and you're standing at the summit. Yeah, and now you can choose to jump down wherever you like. So you can even choose to jump down into online research articles, which don't sound as difficult because you went up and you know what the terms mean. Or you could choose to jump down into more in-depth books on the topic, which is what I did. Or you could choose to jump down into more multimedia presentations on the topic. So this is something I'd like to demonstrate to you that it kind of intimidated me at first as well. So my slide's going to show something slightly weird. I desired a capability of governable bidirectional temporal displacement. So is that English?
Could you say that again, please?
I desired a capability of governable bidirectional temporal displacement. So don't you? Yeah, you guys do, right? Yeah. So that's not English, okay? And this is not normal language. This is scientific language. It's what I'd like to call it. All this sentence means is this.
Yeah.
That's all it means. That's all it means. So you see, it seemed hard, it seemed chunky at first, but when you break it down into its fundamental components, this is all it means. And in my opinion, this is quite a tendency that many scientific articles have, that they like to convolute the message. But this is really just the language of science, and it's one you decipher through knowledge. That's what I found. So enough of the research process, actually. Let's have a look at actual quantum biology of it. So, even my slide doesn't know what quantum biology is. Yeah. Yeah. So as I told you before, it's a lesser known topic, and because of that there were less research materials present relatively. Although there are many research articles on physics and many research articles on biology, the research articles on the actual intersection was kind of dim or quite low in my case. And because of this, there were lesser specialists present in the field. So this also means that the probability of me getting in touch with a specialist was significantly lower. So in fact, I've not been able to get in touch with a specialist live. However, I've been able to, well, luckily for me, they've left a lot of talks for me live on BBC Radio 4, or they've left a lot of multimedia presentations online, which was very nice. But this is really one of the drawbacks of my topic. But I would say that if you're going to choose a topic, don't let this get in your way. If you're interested in it, that's all that matters, if you ask me. It's not that, oh, there's less research material present, so how can I make a project about it? It's more that whether you're interested about it or not. That's what I feel is the strongest factor. So, yeah. Enough of the process. Let's look at the fruits of the research, the juicy part. Yeah. So, I'll start by just giving a brief explanation about quantum entanglement. And I'll start by giving an analogy about quantum entanglement, right? So, I'd like you to consider this. We have two glass panes and an image screen, alright? So the rule here is that you're not allowed to see I'm going to cover the glass panes for you. So you're not allowed to see the color of each glass pane individually, alright? But you do know that if you were to pass light through both the glass panes, you would get a magenta color, alright? So now, the total property of the system is that a magenta color must be produced. And if I were to tell you that glass pane A is red, you could immediately find out that glass pane B must be blue in order to satisfy the total condition that the color produces magenta. And if I were to now tell you that, oh, glass pane A is not red, but glass pane A is blue, it would have to mean that glass pane B is then red instead of glass pane B being blue to satisfy the total property that the color produces magenta. So that's just really entanglement in a nutshell, right? So we're not really looking at those two particles, but these two particles really. So let's see, Ryan here is given a sweet kiss by this damsel here, and when Ryan is given this kiss, Brian, who is nowhere near the scene, feels the kiss as well, and it's because they're both quantum entangled. It's not these two who are quantum entangled; it's these two. Yeah. So when two particles love each other very much, they get quantum entangled. Okay. So now I'm going to just show you quantum entanglement within electrons. Really, quantum entanglement is just a property of a total system, not a property of individual particles, but the property of a total system. And in atoms, here are two electrons very beautifully drawn. So in atoms, electrons are always filled in pairs. And when electrons are filled in pairs, quantum entanglement says that these two electrons have a property, the total spin of these two electrons must add up to 0. What this means is that if one of the electrons is spinning up, the other electron has to be spinning down in order to satisfy the total property that the spin must be 0. So this condition is when the electrons have a different spin. We call that a singlet state. And what happens is that if you were to isolate these electrons or separate them from each other, no matter how far they may be, as long as you keep the conditions the same, they should still be in that singlet state. But if you were to somehow ruin that delicacy by adding Barman there, yeah, you could have, there is a probability of disrupting states now, that you could change the spin of one of the electrons. And what this does is that, yeah, so both electrons now have the same spin, and we refer to this as a triplet state. So this concept is important for reasons I'll show later on. But now, after looking at this phenomenon, we'll just look at the biology part of it. So, yeah, the Sooty Shearwater Puffinus species, italics for the biologists. Yeah, right. So this bird is an adventurer, and it has a migration distance of 64,000 kilometers. So, I mean, how on earth does this bird manage to travel without getting lost? I mean, apart from birds leaving me with unpleasant surprises of stuff on my shoulder, I've not seen birds navigating using a map or anything. I'm very confused. So it turns out that apart from birds using landmarks, they also use magnetic fields. And this was demonstrated in the 1960s using this apparatus here. Adam might not like this. Using this apparatus here called an Emlyn funnel, which is named Emlyn for no apparent reason. It's just basically a funnel, a collapsing funnel. So paper on the sides and ink at the bottom. The idea is you trap a bird without considering his own free will. You trap a bird inside, and you see that his legs get stuck in the ink. And when the bird tries to jump out and escape, he leaves imprints on the paper. And what scientists noticed is that there was a correlation between the number of imprints on the side of the paper and the direction of the magnetic field that they exerted on within the Emlyn funnel. So it's been no mystery that birds do actually react to these magnetic fields. But the real mystery was how exactly they react to these magnetic fields. And yeah, so what we're looking at now is this one, a radical paramechanism. This is it's a model within quantum biology, and it attempts to use quantum entanglement to explain how birds might react to magnetic fields. And the idea is that, as you saw before, the state of the electron is affected by the magnetic field. And if the electrons have a singlet state, or whether they have a triplet state, that can affect the end products of the chemical reaction. This is because triplet states have a higher electron affinity for the chemists here. But now that we have a mechanism to convert this magnetic frequency or magnetic direction into a chemical product distribution, we now have a sort of process of conversion that we could kind of use to convert this magnetic field into signals, ultimately signals that could be sent to the bird's brain, like a sort of cascade effect. So we know about this radical paramechanism, but what we really want to know is where or how it could occur within the bird. And this was looked into by this happy man here named Thorsten Ritz. And what he proposed was that this radical paramechanism occurs within this European robin. And he's pretty much the mascot of quantum biology. I guarantee you, if you went onto Google and you searched for the European robin, you would see pictures of it. If you search for quantum biology, I mean, you would see pictures of him everywhere. So he proposed that this mechanism occurs in the European robin, and more specifically, it occurs in the eyes of the European robin. So within the eye of this European robin, there is this protein called cryptochrome. And this protein, in the presence of blue light, it splits down into two smaller molecules, two free radicals, we like to call them, because each molecule receives one electron from the original cryptochrome molecule. And these two electrons are still quantum entangled, but they could be either be in a single state or a triple state, which is what